cosm. Whoosh.
Look up at the night sky, right now. I mean it. If you could, would you? Because somewhere out there, beyond the twinkling lights of distant suns, beyond the cosmic veil that separates us from the rest of the universe, lies the greatest adventure humanity will ever undertake. And here's the thing that should blow your mind. We're not talking about science fiction anymore. We're talking about actual physics, real mathematics, and engineering challenges that our species is already beginning to tackle. When Christopher Nolan released Interstellar in 2014, audiences around the world watched Cooper pilot his spacecraft through a wormhole, skirt the edge of a massive black hole, and experience time in ways that bent their understanding of reality. But here's what most people don't realize. Nearly everything you saw on that screen was rooted in genuine theoretical physics. Kip Thorne, the Nobel Prize-winning physicist who consulted on the film, wasn't there to make things look cool. He was there to keep the science honest. And that's where our journey begins. Let me take you back to a moment that changed everything. It's 1905, and a 26-year-old patent clerk in Bern, Switzerland, is about to detonate a bomb in the world of physics. His name is Albert Einstein, and he's just figured something out that nobody in human history had understood before. Time and space aren't separate things. They're woven together into a single fabric called space-time, and this fabric can bend, stretch, and warp. Now, before Einstein, we all thought time was this absolute thing. A second in New York was a second in Tokyo, was a second on Mars, was a second at the edge of the observable universe. Tick, tick, tick. Universal clockwork. But Einstein showed us something profoundly different. Time is relative. It depends on how fast you're moving and how deep you are in a gravitational field. And when I say time changes, I don't mean it feels different. I mean actual, measurable, physical time literally runs at different rates. Think about it like this. You're standing on a street corner, and your friend drives past you in a car. To you, standing still, time is flowing normally. But for your friend in the car, time is running ever so slightly slower. Not by much at highway speeds, mind you. We're talking about nanoseconds. But the effect is real, and it's measurable with atomic clocks. Now imagine instead of a car, your friend is traveling at 90% the speed of light. Suddenly, for every year that passes for you, only about half a year passes for them. They come back younger than they should be. This isn't a trick. This isn't a paradox in the traditional sense. This is physics. And here's where it gets wild. Gravity does the same thing. The stronger the gravitational field, the slower time runs. Right now, time is running faster for you than it is for someone standing at sea level if you're on a mountain. The difference is tiny, impossibly tiny for human perception, but GPS satellites orbiting Earth have to account for this every single day. Without Einstein's corrections, your GPS would drift by miles within hours. So when you watch Interstellar and see Cooper's crew descend to Miller's planet, orbiting so close to the supermassive black hole Gargantua that 1 hour there equals 7 years back on Earth, that's not Hollywood exaggeration. That's Einstein's general relativity at work. The math checks out. Kip Thorne calculated it precisely. If you orbit close enough to a black hole of sufficient mass, time dilation becomes so extreme that you could literally watch civilizations rise and fall in what feels like an afternoon to you. Let me paint you a picture of what this means. Imagine you're an astronaut heading toward a black hole. You're approaching the event horizon, that point of no return beyond which nothing, not even light, can escape. To your crewmates watching from a safe distance, you appear to slow down. Your movements become sluggish. Your waving hand takes longer and longer to complete each arc. And here's the really mind-bending part. They never see you cross the event horizon. From their perspective, you freeze there, getting redder and redder as your light gets stretched to longer wavelengths, until you fade from view entirely. But from your perspective, you cross the event horizon in finite time. You don't feel anything special at that moment. The point of no return passes you by, and you continue falling toward the singularity at the center. This is the nature of spacetime near a black hole. It's not just bent. It's tortured into shapes that defy our everyday intuition. And yet, the mathematics describes it perfectly. Einstein's field equations don't care about our intuition. They care about the geometry of spacetime, and they're brutally honest about what happens when mass and energy curve the fabric of reality. Now, let's talk about the big one, the concept that captured imaginations around the world: wormholes. In Interstellar, the crew discovers a wormhole near Saturn, a tunnel through space-time that connects our solar system to a distant galaxy. They fly through it, and boom, they're thousands of light years away, having crossed a distance that should have taken tens of thousands of years in mere moments. Here's the truth: wormholes are mathematically possible. They pop right out of Einstein's equations as valid solutions. A wormhole is essentially a shortcut through space-time, a bridge connecting two distant points. Think of space-time like a sheet of paper. If you want to get from one corner to the opposite corner, normally you'd have to travel across the surface. But what if you could fold the paper so those two corners touch, then punch a hole through? Suddenly, the journey is instantaneous. That's a wormhole. And this is a massive but, mathematics allowing something and nature providing it are two very different things. First, you need exotic matter. Not antimatter, not dark matter, but something even stranger: matter with negative energy density. This stuff would have negative mass and would generate anti-gravity. We've never seen anything like it in nature. Quantum field theory suggests it might exist in microscopic amounts in certain conditions, but scaling that up to make a traversable wormhole big enough for a spacecraft. That's like trying to build a skyscraper out of soap bubbles. Second, even if you could create a wormhole, keeping it open is another challenge entirely. The equations suggest that any wormhole would be catastrophically unstable. The slightest disturbance, even a single photon of light trying to pass through, could cause it to collapse faster than you could say event horizon. To stabilize it, you'd need enormous amounts of this exotic matter arranged in precise configurations around the wormhole's throat. And third, even if you somehow solve those problems, there's the causality issue. A traversable wormhole is, in essence, a time machine. If you can connect 2 points in space, and those points are moving relative to each other, you can arrange things so that you emerge from the wormhole before you entered it, at least from certain reference frames. This leads to all sorts of paradoxes. Could you go back and prevent yourself from entering the wormhole in the first place? Physics doesn't like paradoxes. There are proposals for how nature might prevent these causal violations, but nobody knows for sure. So when you see that gorgeous visual in Interstellar of the wormhole distorting the view of galaxies beyond it, that's actually showing you something accurate. The gravitational lensing, the way light bends around the wormhole's mouth, that's all rendered based on real physics. The visual effects team worked with Kip Thorne to ray trace light paths through the curved spacetime around the wormhole. What you see on screen is what you would actually see if such an object existed. But here's where I want to blow your mind even further. The wormhole in Interstellar appears suddenly, placed there by mysterious beings the characters call they. This might sound like a convenient plot device, but it's actually addressing a profound question. If wormholes require such advanced technology and exotic physics to create, who would make one and why? This brings us to one of the most provocative ideas in all of physics. If time travel is possible through wormholes or other means, where are all the time travelers? Physicist Kip Thorne himself has contributed to this discussion. His work suggests that maybe, just maybe, wormholes can't be used to travel to a time before the wormhole was created. It's like building a time machine today. You could visit any point in the future, but you could never go back to yesterday. This would explain why we're not overrun with tourists from the future. Or maybe the answer is simpler and more sobering. Maybe wormholes simply can't exist in the stable, traversable form we need for interstellar travel. Maybe the universe has a built-in protection mechanism against causal paradoxes. We call this the chronology protection conjecture. It's not proven, but Stephen Hawking was fond of saying that the universe seems to be safe for historians, meaning that paradoxes are somehow prevented by the laws of physics we haven't fully understood yet. Let's shift gears and talk about black holes themselves, because Gargantua, the massive black hole in Interstellar, deserves its own discussion. This isn't just any black hole. It's a supermassive black hole, millions or even billions of times the mass of our Sun, spinning at nearly the maximum rate physics allows. Black holes come in different sizes. Stellar mass black holes form when massive stars collapse at the end of their lives. These typically range from about 3 to a few dozen solar masses. Then there are supermassive black holes, the monsters lurking at the centers of most galaxies, including our own Milky Way. Sagittarius A star, the black hole at the heart of our galaxy, weighs in at about 4 million solar masses. Some supermassive black holes are billions of times more massive than our Sun. Now here's something that blows my mind every time I think about it. The larger a black hole is, the lower its average density. Wait, what? Yes, you heard that right. A stellar mass black hole crams incredible density into a small volume. But a supermassive black hole, while having enormous mass, has an event horizon so large that the average density inside that sphere can be less than water. For the largest supermassive black holes, the average density can be less than air. This has a profound implication for any unfortunate astronaut falling in. For a small black hole, the tidal forces near the event horizon would rip you apart long before you crossed it. We call this spaghettification, and it's exactly as brutal as it sounds. The difference in gravitational pull between your head and your feet becomes so extreme that you'd be stretched into a long, thin strand of atoms. But for a supermassive black hole like Gargantua, the event horizon is so far from the singularity that the tidal forces at the horizon are actually quite gentle. You could cross the event horizon and not feel anything unusual. You'd only notice the increasingly fierce tidal forces as you approached the singularity at the center. And speaking of that singularity, let's address the elephant in the room. What actually is it? A singularity is a point where the mathematics breaks down, where densities become infinite and spacetime curvature becomes infinite. It's where Einstein's equations throw up their hands and say, "I got nothing." But here's the thing. Most physicists don't believe singularities actually exist in nature. We think they're a sign that our theory is incomplete, that there's some deeper physics, probably involving quantum mechanics, that takes over at those extreme scales. This is where quantum gravity comes in. Right now, we have two magnificent theories that describe the universe. General relativity handles the big stuff: planets, stars, galaxies, the curvature of spacetime. Quantum mechanics handles the small stuff: atoms, particles, the probabilistic nature of reality at microscopic scales. But these two theories don't play nicely together. When you try to apply quantum mechanics to gravity, especially in extreme situations like the center of a black hole or the moment of the Big Bang, the math goes haywire. For decades, physicists have been trying to reconcile these theories into a unified theory of quantum gravity. String theory, loop quantum gravity, and other approaches all attempt this unification. None have been definitively proven yet, but whatever the correct theory turns out to be, it will probably tell us that singularities don't exist. Instead, there's some quantum structure, some graininess to spacetime itself at the smallest scales that prevents the infinite densities we get in our current equations. Now let's talk about something you saw vividly in Interstellar: the accretion disk around Gargantua. When matter falls toward a black hole, it doesn't usually fall straight in. It has angular momentum, so it spirals inward, forming a disk of material orbiting the black hole. Friction within this disk heats the material to incredible temperatures, millions of degrees, causing it to emit intense radiation, often in X-rays. In the movie, you see this accretion disk glowing brilliantly, and there's something weird about it. You can see the disk both above and below the black hole simultaneously, even though the disk is actually flat. This isn't an error. This is gravitational lensing in action. The black hole's gravity is so strong that it bends light from the backside of the disk up and over the top, and down and under the bottom, making it visible from angles where you shouldn't be able to see it. This is real physics. The visual effects team at Double Negative spent years working with Kip Thorne to accurately render these light paths. and they actually discovered new features in the equations that theorists hadn't fully appreciated before. The result was so scientifically accurate that Kip Thorne published papers about the visualizations. That's right, a Hollywood movie led to actual scientific publications. How often can you say that? But here's something the movie doesn't show you, for obvious dramatic reasons. The radiation environment around a black hole with an accretion disk would be lethal. The X-rays and gamma rays pouring off that superheated material would fry any astronaut or spacecraft that got too close. In reality, any mission to visit a black hole would need to keep a very safe distance or have radiation shielding so advanced it's beyond our current technology. There's another detail about black holes that Interstellar hints at but doesn't fully explore: frame dragging. When a black hole spins, it literally drags space-time around with it. It's like space-time is a fluid, and the black hole is a spinning ball in that fluid, creating a whirlpool effect. This is called frame dragging or the Lense-Thirring effect, and it's been measured around Earth using satellites. Earth is spinning, so it drags space-time ever so slightly. For a rapidly spinning black hole, this effect is extreme. Near a spinning black hole, there's a region called the ergosphere, outside the event horizon but within a larger boundary called the static limit. Inside the ergosphere, space-time is being dragged around so forcefully that nothing can remain stationary. Everything must rotate with the black hole, whether it likes it or not. But here's the wild part. In principle, you could extract energy from a spinning black hole using this effect. It's called the Penrose process, and it works by dropping something into the ergosphere in just the right way. The object splits into two pieces. One falls into the black hole, and the other escapes with more energy than you started with. The extra energy comes from the black hole's rotation, slowing it down ever so slightly. Could an advanced civilization harvest energy from a black hole this way? In principle, yes. A supermassive black hole could power an entire galactic civilization if you could tap into its rotational energy. This isn't just science fiction. It's a serious proposal considered by physicists thinking about advanced civilizations. Now, let's address the journey itself. In Interstellar, the crew travels to 3 potentially habitable planets orbiting Gargantua. But here's a question. Could planets actually exist in stable orbits around a black hole? The answer is a qualified yes. Black holes aren't cosmic vacuum cleaners. They don't suck everything in. If you replaced our sun with a black hole of the same mass right now, Earth would continue orbiting exactly as it does. The gravitational field far from a black hole is no different from that of any other mass. The problem is formation. Planets typically form from the disk of material around a young star. A black hole doesn't provide the same environment. If there are planets orbiting a black hole, they probably formed around a star and remained after the star collapsed, or they were captured from passing systems. It's possible, but it's not the typical place you'd expect to find planets. And those tidal forces we talked about, they'd be a serious issue. Any planet orbiting close enough to experience extreme time dilation would also experience significant tidal stresses. The planet would be stretched and squeezed, leading to intense geological activity. Think of Jupiter's moon Io with its constant volcanic eruptions driven by tidal heating, but orders of magnitude more extreme. This brings up another challenge shown in the movie. The water world, Miller's planet, with its shallow ocean and massive tidal waves. Those waves are driven by the extreme tidal forces from Gargantua. The water is literally sloshing around the planet like coffee in a cup as the planet orbits. The math for this is complex, but the concept is sound. Tidal forces from a massive nearby object can create exactly this kind of effect. However, let's think about the habitability for a moment. A planet in such an extreme tidal environment, with time running so much slower than the rest of the universe, would face challenges beyond the obvious. Where does the energy come from to maintain a liquid ocean? There's no star providing warmth. The black hole doesn't radiate visible light. The only heat sources would be tidal heating and perhaps radiation from the accretion disk. Could that be enough? Maybe under very specific circumstances. And here's something to consider. On a planet where time runs that slow, evolution would crawl. 1 hour on Miller's planet equals 7 years outside. So for every hour of evolutionary time on Miller's planet, life elsewhere in the universe gets over 60,000 hours. Any life that did start on Miller's planet would evolve at a glacial pace compared to the rest of the universe. Let me take you to Man's Planet, the frozen world where Matt Damon's character waits in cryosleep. This planet is farther from Gargantua, experiencing less extreme time dilation and orbiting in a more stable region. But it's frozen solid, with an atmosphere that's not breathable. This is actually a more realistic scenario for planets in such a system. Without a star's warmth, most planets would be frozen wastelands unless they had some internal heat source or were tidally heated by a black hole or nearby massive planets. The movie touches on something profound here: the desperation of finding a new home for humanity. In the film's backstory, Earth is dying, crops are failing, and dust storms ravage the planet. This isn't far-fetched. Climate change, ecosystem collapse, resource depletion, these are real challenges we face. The question isn't whether we could face such a crisis, but whether we'll solve our problems here on Earth or need to look elsewhere. And that brings us to one of the biggest questions in the movie and in real life. How do we get there? Interstellar uses the wormhole as a shortcut, but what if we didn't have that luxury? What would it take to reach another star system using technology we could plausibly develop? The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. That means if you could travel at the speed of light, which you can't, it would still take 4.2 years to get there. At the speed of our current spacecraft, like the Voyager probes traveling at about 38,000 miles per hour, it would take over 70,000 years. Clearly, we need to go faster, much faster. Let's talk about some real proposals for interstellar travel that don't involve wormholes or exotic physics we haven't discovered yet. First, there's nuclear propulsion. Chemical rockets like the ones that took us to the moon are woefully inadequate for interstellar travel. They're limited by the energy available in chemical bonds, which isn't nearly enough. Nuclear energy, whether from fission or fusion, provides much more energy per unit of fuel. A fusion rocket, if we could build one, could potentially reach a few % of the speed of light. That would get us to Proxima Centauri in maybe a century or so. Still a long journey, but within the realm of possibility for a multi-generation ship or crew in suspended animation. Project Daedalus, a study conducted in the 1970s by the British Interplanetary Society, designed a theoretical spacecraft that could reach nearby stars using nuclear pulse propulsion. The idea was to detonate small nuclear bombs behind the spacecraft and ride the shockwaves. Sounds crazy, but the physics works. The spacecraft could accelerate to about 12% the speed of light, reaching Barnard's star in about 50 years. A more modern proposal is Breakthrough Starshot, announced in 2016 with backing from physicist Stephen Hawking and investor Yuri Milner. The idea is to use powerful lasers on Earth to propel tiny spacecraft equipped with light sails. These starships would be accelerated to 20% the speed of light, reaching Proxima Centauri in about 20 years. The catch? They're small, maybe the size of a postage stamp, carrying only miniaturized electronics. They couldn't carry human passengers, but they could transmit data back to Earth about what they find. But let's dream bigger. What about faster-than-light travel? Einstein's special relativity tells us that nothing with mass can reach or exceed the speed of light. As you accelerate, your mass increases, requiring more and more energy to go faster. To actually reach the speed of light would require infinite energy, which is obviously impossible. However, and this is important, Einstein's general relativity doesn't strictly prohibit faster-than-light travel. Prohibits anything moving through spacetime faster than light. But what if you could manipulate spacetime itself? This is where the Alcubierre drive comes in. In 1994, Mexican physicist Miguel Alcubierre proposed a solution to Einstein's equations that describes a warp bubble. Inside the bubble, spacetime is flat, and a spacecraft sits comfortably. But the bubble contracts spacetime in front of the ship and expands it behind. The ship itself doesn't move faster than light relative to the space immediately around it, but the bubble can move through space at any speed, carrying the ship along with it. It's like riding a wave. The water molecules aren't moving faster than the wave speed limit, but the waveform itself can travel quickly. This sounds perfect. We build our warp drive, engage, and zip off to distant stars. Not so fast. The Alcubierre drive has some serious problems. First, it requires negative energy, the same exotic matter problem we have with wormholes. Second, the energy requirements, even with optimized versions of the original design, are staggering. Early calculations suggested you'd need the mass energy equivalent of Jupiter. Later refinements got that down to something closer to the mass of Voyager 1, but you'd still need to convert that mass entirely to energy and then somehow make it negative energy. Third, there are causality issues again. A warp drive could potentially be used as a time machine. And fourth, recent work suggests that anyone inside the warp bubble couldn't actually control it from inside. You'd need to set up the bubble from outside before getting in. Despite these challenges, NASA's EagleWorks laboratory briefly looked into the physics of warp drives, not because we're about to build one, but because understanding the physics might lead to other discoveries. That's how science works. We explore the boundaries of what's possible, and even when we find something isn't feasible, we often learn something valuable along the way. Another possibility for faster-than-light travel comes from quantum mechanics. Quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and was deeply troubled by it. But could we use entanglement to transmit information faster than light? The answer, frustratingly, is no. While the correlation between entangled particles is instantaneous, you can't use it to send information. The results of measurements on entangled particles appear random until you compare them with measurements on the other particle. And you have to compare them through normal, slower-than-light communication channels. So while entanglement is real and weird and definitely defies our intuition about how reality should work, it doesn't give us faster-than-light communication or travel. Let's come back down to Earth, or rather, back to more realistic near-term possibilities. If we can't go faster than light, and even getting to a substantial fraction of light speed is enormously challenging, maybe the answer is to accept long journey times and figure out how to survive them. This brings us to generation ships, massive spacecraft designed to sustain a human population for multiple generations during a centuries-long journey to another star. The people who arrive won't be the ones who left. It'll be their great-great-great-grandchildren. This concept has been explored in science fiction for decades. But could it actually work? The challenges are immense. You'd need a closed ecosystem capable of recycling everything for centuries. Water, air, nutrients, everything would need to be recycled with near-perfect efficiency. Any losses would accumulate over time. You'd need to maintain genetic diversity in your population to avoid inbreeding. You'd need to preserve knowledge and skills across generations. Imagine the social and psychological challenges of people living their entire lives on a ship, knowing they'll never see the destination or the world their ancestors left. There are also engineering challenges. The ship would need to shield its occupants from cosmic radiation for the entire journey. It would need a power source that could operate for centuries. Nuclear fission or fusion could work, but you'd need enough fuel for the entire journey, which adds mass, which requires more fuel to accelerate, which adds more mass. It's a vicious cycle. One alternative is suspended animation or cryosleep, as shown in Interstellar. If we could safely freeze humans and revive them decades or centuries later, the journey time becomes less of an issue from the traveler's perspective. They'd go to sleep in one solar system and wake up in another. But can we do this? Not yet. We can preserve individual cells and even some tissues through cryopreservation, but freezing a whole human body without causing fatal damage is beyond our current capabilities. Ice crystals form and rupture cell membranes. Even if we use cryoprotectants to minimize ice formation, we don't yet know how to safely thaw a whole human body and restore all its functions. However, there's been progress. Some organisms can survive freezing, Certain frogs, for instance, can freeze solid in winter and thaw in spring, apparently none the worse for wear. They produce glucose and other molecules that act as natural cryoprotectants. If we could understand and replicate these mechanisms in humans, cryosleep might become possible. Another approach is therapeutic hypothermia, where body temperature is lowered to slow metabolism. This is already used in medicine to protect the brain during certain surgeries. Could we extend this to a longer-term hibernation state? Maybe. There's active research on inducing hibernation-like states in animals that don't normally hibernate. If successful, this could be an intermediate step toward true cryosleep. But let's assume we solve the propulsion problem, the life support problem, and the suspended animation problem. We reach another star system. Now what? How do we find a planet we can actually live on? This is where the science of exoplanets comes in, and it's one area where reality has caught up with science fiction in an exciting way. When I was a kid, we knew of exactly 9 planets, the ones in our solar system before Pluto got reclassified. We suspected there might be planets around other stars, but we had no proof. That changed in 1992 with the discovery of planets orbiting a pulsar, and in 1995 with the discovery of 51 Pegasi b, the first planet found orbiting a sun-like star. Since then, we've found thousands of exoplanets. The Kepler Space Telescope alone discovered over 2,700 confirmed planets before its mission ended. The TESS mission is finding more. We now know that planets are common. Most stars have planets. There are probably more planets in the Milky Way than there are stars. And here's what gets me excited. Some of these planets are in the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. Water is essential for life as we know it, so finding planets in the habitable zone is a key first step in finding potentially life-bearing worlds. We've found several particularly interesting candidates. Proxima Centauri b, orbiting the nearest star to our Sun, is in its star's habitable zone. The TRAPPIST-1 system has 7 Earth-sized planets, with 3 in the habitable zone. Kepler 452b, sometimes called Earth's cousin, orbits a sun-like star and is in the habitable zone. The list goes on and is growing. But being in the habitable zone doesn't guarantee habitability. Venus is technically in the Sun's habitable zone, and look how that turned out. A runaway greenhouse effect turned it into a hellish world with surface temperatures hot enough to melt lead and atmospheric pressure equivalent to being a kilometer underwater on Earth. Mars is also arguably in the habitable zone, but it's too small to retain a thick atmosphere, and its lack of a global magnetic field means solar wind has stripped away most of its atmosphere over billions of years. So what makes a planet truly habitable? We need the right size and mass to hold onto an atmosphere but not be so massive that the atmosphere becomes crushing. We need liquid water, which means the right temperature range. We need a magnetic field to protect against radiation. We need plate tectonics to recycle nutrients and regulate the climate over geological timescales. We need the right chemical ingredients. And we probably need a large moon like ours to stabilize the planet's axial tilt and prevent wild climate swings. That's a tall order. Earth might be more special than we think. Or maybe these conditions aren't as rare as they seem. We don't know yet. This is one of the most exciting open questions in astronomy. Now let's talk about detecting life on these exoplanets. We can't just point a telescope at a distant planet and see if there are trees or cities. The planets are too far away and too close to their bright stars. But we can study their atmospheres. When a planet passes in front of its star from our perspective, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us. Different molecules in the atmosphere absorb different wavelengths of light, leaving characteristic fingerprints in the spectrum. By studying these spectra, we can determine what gases are present. This is called transit spectroscopy, and it's how we'll search for signs of life on distant worlds. What would we look for? Oxygen is a good candidate. Earth's atmosphere is about 21% oxygen, and almost all of it is produced by photosynthetic life. Without life continuously producing oxygen, it would react with rocks and disappear from the atmosphere in a few million years. So abundant oxygen, especially in combination with methane, which reacts with oxygen and shouldn't coexist in large quantities without a source replenishing them, would be a strong biosignature. Other potential biosignatures include methyl chloride, dimethyl sulfide, and phosphine. Phosphine recently made headlines when it was tentatively detected in Venus's atmosphere. On Earth, phosphine is produced by anaerobic bacteria and through industrial processes. There's no known abiotic process that produces significant quantities of phosphine on a rocky planet. So if the Venus phosphine detection is confirmed and can't be explained by unknown chemistry, it might be a sign of life in the Venusian clouds. The scientific community is still debating this. More observations are needed. The James Webb Space Telescope, launched in 2021, is revolutionizing exoplanet studies. Its infrared instruments can detect fainter spectral features than previous telescopes, opening up new possibilities for finding biosignatures. Within the next decade or two, we might have our first real evidence of life beyond Earth. And I'm not talking about microbes on Mars or Europa. I'm talking about life on a planet orbiting another star. Imagine that moment. Imagine when scientists announce that they've detected a combination of gases in an exoplanet's atmosphere that can't be explained by any non-biological process. The planet is too far away for us to visit anytime soon, but we'll know we're not alone. How would that change us? How would it change our perspective on our place in the universe? This connects back to Interstellar in a profound way. The movie is ultimately about survival and the search for a new home. But it's also about what makes us human. Our drive to explore, our love for each other, our hope for the future. These themes resonate because they touch something deep in us. Let's talk about one of the most emotionally powerful scenes in Interstellar. When Cooper watches decades of video messages from his children after returning from just a few hours on Miller's planet. Time dilation has turned hours into years, and he watches his kids grow up without him. This is science being brutally honest about the cost of relativity. If we ever venture out into the universe, we'll face these consequences. The people who explore will become unstuck in time from everyone they know. There's a certain poetry to this. We're already unstuck in time from our ancestors. We can't talk to them, can't share our lives with them. In a relativistic journey, this separation becomes spatial as well as temporal. The explorers become their own sort of time travelers, hurtling forward into the future while everyone they knew ages or dies. But here's a twist that the movie hints at but doesn't fully explore. To an observer back home, the travelers appear to age slowly. But to the travelers, it's everyone back home who appears to be living life in fast forward. Both perspectives are equally valid. There's no absolute frame of reference. This is the heart of relativity, and it's profoundly unsettling to our intuitive notions of a shared, universal now. Now, I want to address one of the more controversial aspects of Interstellar, the Tesseract sequence where Cooper finds himself inside a five-dimensional space behind Murph's bookshelf, able to interact with his past through gravity. Is any of this scientifically plausible? Well, it depends on how charitable we want to be with the interpretation. Let's start with the idea of higher dimensions. Our everyday experience involves three dimensions of space: length, width, and height. Einstein showed us that time is intimately connected to these three dimensions, forming four-dimensional spacetime. But could there be additional spatial dimensions beyond the three we perceive? String theory, one of the leading candidates for a theory of quantum gravity, suggests there could be as many as 10 or 11 total dimensions. The extra dimensions beyond our familiar four would be compactified, curled up so small that we don't notice them in everyday life. Could an advanced civilization manipulate these higher dimensions? In principle, if they exist and if we could access them, yes. From a higher dimensional perspective, events that seem separated in our four-dimensional spacetime might be adjacent. Imagine a two-dimensional being living on the surface of a piece of paper. 2 points on opposite sides of the paper seem far apart to this being, which has to travel across the surface. But a three-dimensional being could fold the paper and bring those points together, or even reach through the paper to connect them directly. The Tesseract sequence in Interstellar is a visualization of this concept. Cooper, with the help of advanced beings, heavily implied to be future humans, accesses a higher dimensional space from which different moments in his daughter's room are adjacent. He can see across time as we might look across space. And he can interact with his past self through gravity, the one force that, in the movie's logic, propagates through all dimensions. Is this scientifically accurate? The honest answer is we don't know. We don't have experimental evidence for higher dimensions beyond the four we can observe. We don't know if gravity can propagate through such dimensions in a way that would allow this kind of interaction. And we don't know if causality paradoxes would prevent this kind of past interaction even if the physics otherwise allowed it. But here's what I love about this sequence. It's asking deep questions about the nature of time and causality. In Einstein's relativity, past, present, and future all exist equally. There's no universal now sliding forward through time. The entire history of the universe, from the Big Bang to the last dying star, exists as a four-dimensional structure called the block universe. Our experience of time flowing is a psychological phenomenon, not a fundamental feature of physics. If we take this seriously, then in some sense the past still exists and the future already exists. You just can't access them because you're constrained to move forward through time. But a being with access to a higher dimension might not be so constrained. They might be able to view time the way we view space, moving back and forth at will. This leads to paradoxes, which I mentioned earlier. If you can change the past, what happens to the version of you that experienced the unchanged past? The movie sidesteps this with a self-consistent time loop. Cooper only manages to communicate with young Murph because adult Murph, his daughter, played by Jessica Chastain and later Ellen Burstyn, figures out that the ghost in her childhood room was her father all along, and she decodes the message he's sending through gravitational anomalies. Everything that happens has always happened. There's no moment where the past changes. It's consistent, if mind-bending. This is known as the Novikov self-consistency principle, proposed by physicist Igor Novikov. The idea is that if time travel or past interaction is possible, the universe somehow arranges things so that paradoxes are avoided. You can travel to the past, but you can't change it in a way that would prevent you from traveling to the past in the first place. Any attempt to create a paradox fails, perhaps in surprising ways. Is this how the universe actually works? We don't know. It's a possibility consistent with what we know, but so is the possibility that time travel and past interaction are simply impossible. Nature has ways of enforcing its rules, and we're still learning what those rules are. Let's shift to another key element in Interstellar: gravity. The movie takes seriously the idea that gravity might be special, that it might be the key to understanding the universe and even to communicating across space-time. There's a reason for this emphasis, and it comes from real physics. In Einstein's general relativity, gravity isn't a force in the traditional sense. It's the curvature of space-time caused by mass and energy. When you're standing on Earth, you're not being pulled down by a force. You're trying to move in a straight line through space-time, but Earth's mass curves space-time in such a way that a straight line leads toward the planet's center. The ground stops you from following that path, and you experience that as weight. This is a radical reconception of gravity, and it leads to predictions that Newtonian physics couldn't make. Gravity should bend light because light follows the curvature of space-time. This was confirmed in 1919 when Arthur Eddington measured the bending of starlight during a solar eclipse. Gravity should create time dilation, as we discussed. Gravity should produce waves, ripples in space-time itself, when massive objects accelerate. This was confirmed in 2015 with the first direct detection of gravitational waves from merging black holes. Gravitational waves are particularly important. They propagate at the speed of light, carrying information about the events that created them. The collision of two black holes releases more power in gravitational waves, for a brief moment, than all the stars in the observable universe emit in light. These waves stretch and squeeze spacetime as they pass through, and we can detect them with incredibly precise instruments like LIGO and Virgo. In Interstellar, Professor Brand, played by Michael Caine, is trying to solve an equation that would let humanity harness gravity, enabling them to lift entire cities off Earth's surface. The movie suggests that understanding quantum gravity, reconciling general relativity with quantum mechanics, is the key. This is accurate in spirit, if not in specifics. Quantum gravity is one of the holy grails of theoretical physics. We know general relativity works for large objects and quantum mechanics works for small objects, but we don't have a complete theory that covers both regimes at once. Why do we need quantum gravity? Because in extreme situations, both quantum effects and gravitational effects are important. Inside a black hole, approaching the singularity, space-time curvature becomes extreme, a relativistic effect. At incredibly small scales, a quantum regime. At the moment of the Big Bang, the entire universe was compressed to subatomic sizes with immense energy densities. To understand these situations, we need a theory that seamlessly incorporates both quantum mechanics and gravity. String theory is one attempt at this. In string theory, particles aren't point-like objects but tiny vibrating strings. Different vibration modes correspond to different particles. One particular vibration mode corresponds to the graviton, the hypothetical quantum particle that mediates gravity. String theory naturally includes gravity and potentially unifies it with the other forces of nature. But string theory has challenges. It requires extra dimensions which we haven't detected. It makes few testable predictions with current technology. And there are a huge number of possible string theory solutions, maybe 10 to 500 or more, leading to the landscape problem. Loop quantum gravity is another approach. It quantizes spacetime itself, suggesting that at the smallest scales, space is made of discrete loops woven together in a network. Time emerges from the changing relationships between these loops. Loop quantum gravity is more conservative in some ways, staying closer to general relativity, but it's less obviously compatible with the standard model of particle physics. There are other approaches too: causal set theory, asymptotic safety, entropic gravity, and more. We don't yet know which, if any, is correct. What we do know is that quantum gravity will probably reveal something profound about the nature of reality at its deepest levels. In the context of Interstellar, the idea is that understanding quantum gravity would let us manipulate gravitational fields in unprecedented ways. Could we really use this to lift cities into space? That's speculative, to say the least. But if we could generate and control strong gravitational fields, the applications would be revolutionary. Not just for spaceflight, but for energy, for fundamental research, for technologies we can't even imagine yet. There's another layer to Interstellar's themes that deserves attention: the role of time and love. The movie famously includes a scene where Brand suggests that love might transcend dimensions, that it might be a quantifiable, observable phenomenon that we don't yet understand. This is poetry, not physics, but it's probing something interesting. We understand the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Love isn't a force in this physical sense. It's an emergent phenomenon arising from the complex interactions of neurons, chemistry, evolution, and culture in our brains. But emergent phenomena can be real and powerful. Consciousness is emergent, yet it's the most immediate and undeniable aspect of your reality. You are conscious. That's as certain as anything can be. Could there be something about emotional bonds, about the connections between minds, that relates to the fabric of reality in ways we don't understand? This is speculative, bordering on mystical, but it's not entirely without precedent in physics. Quantum entanglement creates connections between particles that seem to defy our intuition about separateness. Measure one entangled particle, and you instantly know something about its partner, no matter how far away it is. Einstein found this deeply troubling, but experiments have confirmed it again and again. I'm not saying love is quantum entanglement. That would be an unfounded leap. But I am saying that the universe is stranger than we imagine, and we should be humble about what we don't know. Phenomena we now understand through science were once mysteries or miracles. Magnetism, lightning, the motion of the planets, these were once beyond explanation. Now they're homework problems. Maybe someday we'll have a complete theory of consciousness, a full understanding of how subjective experience arises from objective physical processes. Maybe that theory will reveal something unexpected. Or maybe the divide between objective and subjective is more fundamental than we realize. These are open questions at the intersection of physics, neuroscience, and philosophy. What Interstellar does beautifully is weave these scientific and emotional threads together. The time dilation isn't just a cool visual effect. It has emotional weight, tears families apart. It makes love heartbreaking. The science serves the story, and the story illustrates the science's human implications. Now let's talk about some practical concerns for interstellar travel that Interstellar addresses but perhaps doesn't fully explore. One is the hazard of space debris. At relativistic speeds, even a tiny particle hitting your spacecraft carries enormous energy. A grain of sand hitting a ship traveling at 90% the speed of light would impact with the energy of a nuclear bomb. How do you protect against that? One proposal is to use a magnetic shield to deflect charged particles. Another is to send a sacrificial vanguard ahead to clear the path, perhaps a small, cheap probe that absorbs or deflects debris. Yet another idea is to use a thick shield of some material, maybe ice or rock, absorbing impacts. But all of these add mass, reducing your acceleration and top speed. It's another engineering challenge without an obvious solution. There's also the problem of navigation. At high speeds, you need to know exactly where you're going and adjust your trajectory with incredible precision. A tiny error could make you miss your target star by billions of miles. You'd need real-time data about the positions and motions of stars and any obstacles in your path. And if you're traveling for decades or centuries, the stars will have moved significantly by the time you arrive. You need to aim not for where the star is, but where it will be. Communication is another issue. If you're light years from Earth, even at the speed of light, messages take years to arrive. A message sent from Proxima Centauri takes 4.2 years to reach Earth. The reply takes another 4.2 years to get back. That's over 8 years for a round-trip conversation. For more distant stars, it's even worse. If something goes wrong, you're on your own. There's no calling home for help. This isolation is a recurring theme in stories about space exploration, and it's grounded in hard reality. The speed of light isn't just fast. It's the ultimate speed limit, and it's also maddeningly slow on cosmic scales. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes about 2.5 million years to reach us. That galaxy is in our cosmic backyard. The observable universe is about 93 billion light-years across. The universe is vast beyond human comprehension, and the speed of light, for all its incredible swiftness, is inadequate for crossing those distances in a human lifetime. This is why we keep coming back to ideas like wormholes and warp drives. Not because we know they're possible, but because without something like them, the universe remains mostly beyond our reach. We could colonize our local stellar neighborhood, maybe within a few dozen or 100 light years, with generation ships or cryosleep. But the rest of the galaxy, much less the universe, remains out of reach unless we find a loophole in physics. Let me tell you about another theoretical possibility that Interstellar doesn't explore: the Krasnikov tube. This is another solution to Einstein's equations, proposed by Russian physicist Sergei Krasnikov. The idea is to create a tube of distorted spacetime connecting 2 points. As you travel through the tube at normal, slower than light speeds, the tube itself is manipulated so that the return journey is much shorter. On the outbound trip, you travel at conventional speeds, perhaps taking centuries. But you're using your advanced technology to manipulate spacetime behind you, creating a shortcut. On the return journey, the trip that took centuries outbound now takes days or weeks. This doesn't help the first generation of explorers on the outbound trip. but it means they can return to Earth's time frame and that subsequent travelers can use the tube both ways. Over time, a network of Krasnikov tubes could connect multiple stars, creating a rapid transit system through the galaxy. Like wormholes and warp drives, Krasnikov tubes require exotic matter and enormous energy. They might also have causality issues, but they're another example of physicists pushing the boundaries of theory, exploring what might be possible even if it's far beyond current technology. There's a certain mindset required to think about these problems. You have to be willing to entertain ideas that seem absurd, to follow the mathematics wherever it leads, even into strange territories. At the same time, you have to maintain scientific rigor, distinguishing between what's mathematically possible and what's physically realizable. This is the tightrope that theoretical physicists walk. On one side is wild speculation disconnected from reality. On the other side is timid incrementalism that never takes risks. The sweet spot is bold ideas constrained by the evidence and mathematics we have, open to revision when new data arrives. Interstellar captures this spirit. It's ambitious and imaginative, but it respects the science. When it does speculate beyond known physics, in the Tesseract sequence for instance, it does so in a way that's internally consistent and thematically meaningful. This is science fiction at its best, using the tools of science to explore human questions. Let's talk about another element of the movie, the robots TARS and CASE. These boxy, reconfigurable machines exhibit a level of artificial intelligence and personality that's currently beyond our capabilities but might not be forever. One of the most endearing aspects of TARS is its humor setting, which Cooper adjusts from time to time. This acknowledges something important. AI doesn't have to be human-like to be intelligent or useful. Real artificial intelligence is advancing rapidly. Machine learning algorithms can now beat humans at chess, Go, and various video games. They can recognize faces, translate languages, drive cars, diagnose diseases, and generate art and text. But these are narrow AI specialized for specific tasks. They don't have general intelligence, the ability to flexibly adapt to new situations and learn new skills the way humans do. Artificial General Intelligence, or AGI, remains a goal rather than an achievement. When and if we create AGI, it would be a transformative moment in human history. An intelligence not limited by biological constraints, capable of thinking faster and accessing vast amounts of information instantaneously, could solve problems we can't. It could design better AI, leading to recursive self-improvement and possibly an intelligence explosion. This is both exciting and terrifying. An AGI aligned with human values could help us solve climate change, cure diseases, explore the universe, and achieve feats we can barely imagine. An AGI with goals misaligned with ours could be catastrophic. This is why AI safety research is so important. We need to ensure that as AI becomes more capable, it remains beneficial and controllable. In the context of interstellar exploration, AI would be invaluable. An AI could manage complex spacecraft systems, make decisions faster than humans, and operate independently during long communications delays. For an interstellar probe, especially a small one like those proposed in Breakthrough Starshot, AI might be the only practical intelligence on board. But there's a philosophical question here. If we send AI to explore the stars on our behalf, is that the same as us exploring the stars? Is there something essential about the human experience that can't be captured by a machine proxy? This is another theme lurking in Interstellar, the irreplaceable value of human consciousness and emotion. Let me take a step back and talk about the biggest challenge of all: motivation. Why would we go to the stars? What drives us to explore? In Interstellar, it's survival. Earth is dying, and humanity needs a new home. But what about in real life? What about in a future where Earth is healthy and humanity is thriving? Would we still reach for the stars? I think we would, because exploration is part of who we are. Humans have always explored. We crossed oceans in fragile boats. We climbed the highest mountains. We ventured into the frozen poles. Not because we had to, but because we were curious, because there was a horizon and we wanted to see what lay beyond it. This drive has practical benefits. Exploration leads to discovery, and discovery leads to technology and knowledge that improve our lives. The Apollo program, which put humans on the moon, spun off technologies that led to advances in computing, material science, telecommunications, and medicine. The knowledge we gained about Earth by looking at it from space revolutionized our understanding of climate, ecology, and geology. But beyond the practical benefits, there's something deeper. We explore because it's an expression of human hope and ambition. It's a declaration that we refuse to be confined, that we're not content with what is, that we dream of what could be. In a universe that's indifferent to our existence, our acts of exploration and creation are assertions of meaning. We matter because we decide to matter, because we reach out and touch the cosmos and say, "We were here, we saw, we wondered." Interstellar understands this. The movie is ultimately optimistic. Humanity faces a crisis, but we don't give up. We take insane risks. We venture into the unknown, and we survive. More than that, we transcend. The movie suggests that future humanity, evolved beyond our current understanding, reaches back to save itself, creating a closed causal loop that ensures our survival and evolution. Is this possible? The science is speculative, but the sentiment resonates. We are the product of billions of years of evolution, of physics playing out across cosmic scales. We're made of atoms forged in the cores of stars. We are literally stardust, organized into a pattern that can think and feel and wonder about its origins. That's extraordinary. And it's not unreasonable to imagine that we might continue to evolve, to change, to become something more than we are now. What might future humanity look like? If we spread to the stars, we'll encounter different environments, different selective pressures. We might diverge into multiple species, each adapted to their home world. We might merge with our technology, becoming post-human or transhuman. We might upload our minds into computers, becoming digital entities unbounded by biology. These ideas are speculative, but they're grounded in trends we can already see. Genetic engineering, cybernetics, brain-computer interfaces, virtual reality. The future is uncertain, but it's ours to shape. That's both a burden and an opportunity. The choices we make now, how we handle climate change, how we develop AI, how we govern ourselves, how we treat each other, will determine what the future looks like. Will we survive long enough to become an interstellar species? Will we thrive? Will we create something beautiful and lasting? Or will we destroy ourselves in short-sighted conflicts? Interstellar doesn't give easy answers, but it does give us a vision of resilience and hope. Even when faced with existential threats, humans find a way. We innovate. We cooperate. We sacrifice for each other. And we persist. Let me bring this back to the here and now. We're living in an extraordinary time for space exploration. In my lifetime, we've gone from imagining planets around other stars to discovering thousands of them. We've landed rovers on Mars and flown a helicopter there. We've sent probes to the outer solar system, to comets and asteroids, even into interstellar space. Voyager 1 and 2 have left the solar system, carrying messages from Earth to any intelligence that might find them. We're planning to return to the moon, this time to stay. The Artemis program aims to establish a permanent lunar presence. From there, we'll go to Mars. Elon Musk's SpaceX is developing Starship, a fully reusable rocket designed to carry humans to Mars and beyond. NASA, ESA, China, and other space agencies have ambitious plans for the next few decades. We're also making progress on the technologies needed for interstellar travel. Fusion energy research is advancing. Breakthrough Starshot is testing light sail technology. AI is becoming more capable. Our understanding of exoplanets is deepening. We're taking the first steps. Will we reach the stars in my lifetime? Probably not with humans. But we might send probes. We might discover signs of life on exoplanets. we might take the crucial steps that make interstellar travel possible for future generations. And that's okay. Exploration is a multi-generational endeavor. The cathedrals of medieval Europe took centuries to build. The people who laid the foundations knew they'd never see the finished structure. But they built anyway because they believed in something larger than themselves. Interstellar travel might be the same. We might be laying the foundations for a journey our descendants will complete. There's a moment near the end of Interstellar that always gets me. Cooper, having survived the impossible, having fallen into a black hole and emerged through the Tesseract, is reunited with his daughter Murph on her deathbed. She's an old woman, surrounded by her children and grandchildren. He's barely aged, thanks to time dilation. And she tells him to go, to leave, to find Brand, who's alone on another planet preparing humanity's new home. She tells him, no parent should have to watch their child die. It's a moment of profound sadness and love, but it's also about letting go, about passing the torch. Murph has lived a full life. She solved the equation. She saved humanity. And now it's time for the next generation to continue the work. Cooper goes not because he's running from loss, but because there's still exploring to do, still work to be done, still hope for the future. This is the spirit we need for the challenges ahead. Courage, curiosity, love, and hope. The universe is vast and indifferent, but we are not. We care, we strive, we dream, and in dreaming, we make those dreams real. So let me leave you with this thought. The real Interstellar isn't just about wormholes and black holes and time dilation, though those are part of it. It's about the human spirit. It's about looking up at the stars and deciding that the distance between us and them is a challenge, not a barrier. It's about believing that we can do impossible things, that we can learn and grow and reach beyond ourselves. It's about recognizing that we're part of something larger, a universe that's been unfolding for 13.8 billion years and will continue long after we're gone. But that right now, in this moment, we're here, we're alive, and we can choose what to do with that. The science tells us what's possible. The engineering tells us how to get there. But it's the human element, the love and determination and sheer stubborn refusal to accept limits, that will actually take us to the stars. And maybe, just maybe, when we get there, we'll find that the journey changed us in ways we couldn't have predicted, that we became more than we were, that we fulfilled the potential that's been inside us since our ancestors first looked up at the night sky and wondered what those lights were. The universe is waiting. Not patiently, the universe doesn't care about our timeline. But it's there, vast and full of wonders, ready to reveal its secrets to anyone curious and brave enough to look. And we are curious. We are brave. We are the species that walked on the moon, that sent our machines to the edge of the solar system, that split the atom and mapped the genome and painted the Sistine Chapel and wrote symphonies and built cathedrals and created the internet and landed a rover on Mars. We are capable of amazing things. The question isn't whether we can reach the stars. The question is, will we choose to? Will we invest the time, the resources, the decades or centuries of effort required? Will we make it a priority, or will we turn inward, consumed by short-term concerns, letting the dream die? That's up to us. That's up to you. Because the future isn't written yet. We're writing it right now with every choice we make, every policy we support, every child we inspire to study science and engineering, every dream we dare to dream. So dream big. Look up at the stars. Know that everything I've told you, all this science, all these theories, they're not just abstract ideas. They're maps to actual places, guides to real physics, invitations to adventure. Somewhere out there, maybe there's a planet orbiting a star where life has taken hold, where minds very different from ours are also looking up at their night sky and wondering if they're alone. Wouldn't it be something if we could meet them someday? If we could share our stories, compare our physics, learn from each other? Or maybe we're alone. Maybe in all this vast universe, life is so rare that we're the only ones. If that's true, then we're even more precious. We're the universe's way of knowing itself. We're the eyes through which the cosmos sees its own grandeur. And that means we have a responsibility not just to survive, but to flourish, to spread, to fill the universe with life and thought and wonder. Either way, alone or in company, the journey matters. The exploration matters. The science matters. Not because it gives us neat gadgets or powerful weapons, though it does those things. It matters because it tells us the truth about reality, and truth is worth pursuing for its own sake. It matters because it expands our horizons, literally and figuratively. It matters because it reminds us that we're small in the cosmic scale but not insignificant, that our brief flicker of existence is part of a grand tapestry that stretches from the Big Bang to the heat death of the universe and beyond. Every atom in your body is billions of years old. The hydrogen atoms were created in the Big Bang. The heavier elements were forged in stars and scattered by supernovae. You are ancient. You are connected to the deepest history of the universe. And you're here now, able to understand that history, able to wonder about your place in it. That's not an accident. That's evolution and physics and chemistry conspiring over billions of years to create something capable of understanding itself. So when you watch Interstellar, or read about black holes, or hear about the discovery of a new exoplanet, remember, this isn't just entertainment or trivia. This is your story. This is the story of where you came from and where you might go. This is the story of a species that refused to be bound by the surface of its birth planet, that looked up and decided that up was the direction to go. We haven't reached the stars yet. We might not reach them for centuries, but we will reach them if we choose to, if we persist, if we remember why exploration matters. And when we do, when human beings or our descendants or the AI we've created or some fusion of all three finally stand on a planet orbiting another star and look back at the pinpoint of light that is our sun, they'll remember this moment. They'll remember that we dreamed it first, that we did the math, that we took the first steps. The universe is 13.8 billion years old. It will exist for trillions of years to come. In that vast span, our species' existence is a brief moment. But it's our moment, and what we do with it matters, at least to us, and maybe that's enough. Maybe meaning isn't something we find in the universe. Maybe it's something we create by caring, by striving, by loving each other and loving the quest for knowledge and loving the beauty of a spiral galaxy or a mathematical equation or a child's first question about why the sky is blue. Interstellar gets this right. It's not just a movie about space travel. It's a movie about love and loss and hope and sacrifice. It's about the science, yes, but it's also about why the science matters, why we do this at all. And the answer is for each other, for our children, for the future, for the sheer audacious joy of knowing something true about the universe. So the next time you look up at the night sky, think about everything that's out there. Think about the black holes and the exoplanets and the distant galaxies. Think about the physics that governs it all, the elegant mathematics that describes reality. And think about the fact that you, a pattern of organized matter, can understand these things. You can look at a galaxy billions of light years away and know how old it is, how fast it's moving, what it's made of. That's incredible. You are incredible. We are incredible. And we're just getting started. The age of exploration isn't over. It's barely begun. We've explored our planet, and now we're starting to explore our solar system, and soon, eventually, inevitably, we'll explore the galaxy. The journey will be long. It will span generations. It will require sacrifices. But it will be worth it because it's what we do. We explore. We discover. We push boundaries. We reach for the stars, literally and metaphorically. This is the real Interstellar. Not the movie, though the movie captures it beautifully. The real Interstellar is the ongoing human project of understanding and exploring the universe. It's happening right now in laboratories and observatories around the world. It's happening in the minds of children who look up and wonder. It's happening in the equations of physicists pushing the boundaries of knowledge. It's happening in the spacecraft we're sending to distant worlds. It's happening every time someone asks, why? Or how? Or what if? You're part of it. By being curious, by learning, by caring about these questions, you're contributing to humanity's greatest adventure. You don't need to be an astronaut or a physicist. You just need to look up, to wonder, to imagine what might be possible. Because before we do anything, before we build anything, before we discover anything, we have to imagine it. We have to dream it. So dream. Dream of starships and distant worlds. Dream of discoveries that will change everything. Dream of a future where humanity thrives, where we've solved our problems, where we've spread beyond Earth. Dream of meeting other minds in the universe, or of being the first, the special ones, the universe's children venturing out to make their mark. Dream of understanding everything, of having a final theory of physics, of knowing the universe as deeply as it can be known. Dream of time travel and wormholes and technologies we can't yet imagine. Some of those dreams will come true, some won't, but the dreaming itself matters. It's what drives us forward. And sometimes, just sometimes, the impossible becomes possible. We split the atom, which seemed impossible. We went to the moon, which seemed impossible. We eradicated smallpox, which seemed impossible. We'll tackle climate change, which seems impossible. And one day, somehow, we'll reach the stars, which seems impossible now but won't be forever. That's the message of Interstellar, and it's the message of science itself. The universe is knowable, reality is understandable, and we can do hard things. We can face impossible challenges and overcome them. Not easily, not quickly, but we can do it. Together, with science and courage and hope and love. The stars are waiting. They've been waiting for billions of years, and they'll wait for billions more. But they're there, and they're ours to explore if we choose to. And I think we will choose to because we always have. Because we're humans, and exploring is what we do. So here's to the dreamers and the doers, the scientists and the engineers, the astronauts and the mission controllers, the children who look up and wonder and the adults who never stopped wondering. Here's to the quest for knowledge and the thrill of discovery. Here's to the universe in all its vast, strange, beautiful glory. And here's to us, the unlikely species on an unremarkable planet orbiting an ordinary star, who looked up at the cosmos and decided to understand it. We're going to the stars. Maybe not today, maybe not tomorrow, but eventually. And when we get there, when we stand on an alien world under an alien sun and look up at an alien night sky, we'll remember this moment, this time when we were just beginning, when we were figuring it all out, when we were taking our first steps toward becoming a truly interstellar species. The journey of 1,000 light years begins with a single step. We've taken that step. We've left Earth. We've touched the moon, sent our robots to Mars and beyond, peered into the depths of the universe with our telescopes. We know so much more than we did a century ago, and we'll know so much more a century from now. The acceleration of knowledge is itself accelerating. We're on an exponential curve of discovery and capability. Where will it lead? Nobody knows for certain, but if history is any guide, it will lead to places and achievements beyond our current imagination. Our ancestors couldn't have conceived of the internet or quantum computers or gravitational wave detectors. Our descendants will have capabilities we can't conceive of, and they'll use those capabilities to explore, to discover, to create, to push ever further into the unknown. That's our legacy. That's what we're building, not just for ourselves, but for the future, for all the generations to come, for the humans and post-humans and AIs and whoever else emerges from our lineage. We're starting something that will outlast us by millennia, maybe by millions of years. We're initiating the spread of Earth-originated life and intelligence into the cosmos. That's a profound responsibility and an incredible privilege. So let's do it right. Let's be thoughtful and careful and wise. Let's protect our planet while we learn to live on others. Let's develop our technology while ensuring it serves our values. Let's reach for the stars while keeping our feet grounded in compassion and ethics. Let's be the species that figured it out, that navigated the challenges of the 21st century and emerged stronger, ready to take on the universe. The real Interstellar isn't a movie or a distant dream. It's a project we're engaged in right now. Every launch, every experiment, every discovery is a step toward that future. And you're part of it. By learning, by caring, by supporting space exploration and scientific research, by inspiring others, you're contributing. You're helping to write the next chapter in humanity's story. And what a story it is. From the savannas of Africa to the surface of the moon to the edges of the solar system and beyond. From wondering about the lights in the sky to understanding them as distant suns with their own planetary systems. From thinking Earth was the center of everything to realizing we're on an ordinary planet in an ordinary galaxy in a universe containing hundreds of billions of galaxies. It's a story of expanding horizons and growing knowledge and increasing humility about our place in the cosmos, combined with increasing pride in our ability to understand it. We are the species that does science. We are the species that explores. We are the species that asks why. And we won't stop. We can't stop. It's in our nature. We're driven by curiosity and ambition and hope. We're driven by the desire to know, to understand, to explore. And that drive will take us to the stars one way or another, in one form or another, sooner or later. The universe is vast and ancient and will continue long after we're gone. But right now, in this brief cosmic moment, we're here. We're alive. We're thinking and feeling and wondering. And that's enough. That's everything. We don't need to conquer the universe or leave our mark on every planet. We just need to be ourselves, to do what we do best. Ask questions, seek answers, push boundaries, reach for the impossible. The real interstellar is humanity's journey from ignorance to knowledge, from Earth to the stars, from isolated and alone to connected and understanding. It's a journey we're in the middle of, a journey that will continue for as long as our species or its descendants exist. And it's the greatest adventure in history, the ultimate quest, the final frontier. So buckle up, study hard, stay curious, support science, dream big, because the universe isn't going to explore itself. It needs us. It needs curious minds and brave hearts and determined spirits. It needs dreamers who look up and imagine what might be possible and then set about making it real. The stars are waiting. The universe is waiting. The future is waiting. And it's ours to create together, one discovery at a time, one mission at a time, one generation at a time. The real interstellar starts now, with you, with me, with all of us looking up and deciding that distance is just a number, that impossible is just a challenge, that the universe is ours to explore. Let's go. But before we reach those distant stars, we need to master our own cosmic neighborhood. And that brings us to something Interstellar doesn't show you: the intermediate steps. You don't just wake up one morning and build a starship. You practice. You learn. You make mistakes closer to home where those mistakes aren't fatal to the entire species. Right now, humanity is learning to become a spacefaring civilization, and we're doing it the hard way. We're sending robots to Mars, and those robots are teaching us lessons that will save lives when humans finally make the journey. Spirit, opportunity, curiosity, perseverance. These rovers aren't just scientific instruments. They're scouts. They're teaching us about Martian dust and how it clogs mechanisms. They're teaching us about the radiation environment and the temperature swings and the challenges of autonomous operation with communication delays. Mars is our testing ground. It's close enough that we can get there in 6 to 9 months with current propulsion technology. It's far enough that it presents real challenges. And it's similar enough to Earth that we can imagine living there, but different enough that we have to solve hard problems to make it work. Let me tell you what it's really like on Mars, because the movies never quite capture it. The atmosphere is less than 1% the density of Earth's at sea level. You can't breathe it, obviously, but you also can't use it for much of anything. Parachutes barely work. Sound travels differently. The low atmospheric pressure means water can't exist as a liquid on the surface. It either freezes or boils away depending on the temperature. And speaking of temperature, Mars is cold. The average temperature is around -80 degrees Fahrenheit. Even at the equator in summer, it barely gets above freezing during the day, then plummets at night. The gravity is about 38% of Earth's. That sounds fun until you realize what it means for your body. Your bones will lose density. Your muscles will atrophy. Your cardiovascular system will adapt to the lower gravity, and then if you ever want to return to Earth, you'll have to recondition for months. The human body evolved for Earth gravity. We're not built for Mars. We can adapt, but it comes at a cost. And then there's the radiation. Mars has no global magnetic field and barely any atmosphere to speak of. This means cosmic rays and solar radiation hit the surface with much greater intensity than on Earth. An astronaut on Mars would receive about 200 times the radiation dose of someone on Earth. Over a year, that adds up to a dose that significantly increases cancer risk. We'll need shelter, probably underground, to protect settlers from this constant bombardment. But here's what's exciting. These are all solvable problems. Hard problems, yes, but not impossible ones. We can build habitats with radiation shielding. We can grow food in greenhouses using Martian soil supplemented with nutrients from Earth. We can extract water from the ice we know exists beneath the surface. We can even make rocket fuel from Martian carbon dioxide and water using the Sabatier reaction, turning Mars into a refueling station for further exploration. Elon Musk envisions 1 million people living on Mars by the end of this century. Is that realistic? Maybe, maybe not. But the audacity of the vision is important. It forces us to think big, to plan for scale, to develop technologies that can support a self-sustaining civilization on another world. Whether it's 1 million people or 1,000 or 100, the principle is the same. We're learning to live beyond Earth. And Mars is just the beginning. The Moon is closer and easier to reach, and we're going back there with the Artemis program. This time, we're not just planting flags and collecting rocks. We're building infrastructure. A lunar base could serve as a staging ground for missions to Mars and beyond. The Moon has resources we can use: water ice at the poles, helium-3 in the regolith that could potentially fuel fusion reactors, and of course, an abundance of rock and metal for construction. There's also the psychological preparation. Long-duration missions to the Moon and Mars will teach us about the human factors of space exploration in ways we can't fully predict. How do people cope with isolation, confinement, and constant danger? How do small groups maintain cohesion over months or years? What happens to the human psyche when you look up and see an alien sky, when you know that there's nothing between you and the void except a thin wall of metal and polymer? We've studied some of these questions with the International Space Station, which has been continuously occupied since the year 2000. Astronauts have spent up to a year aboard the ISS, and we've learned a lot about the medical and psychological challenges of long-duration spaceflight. We know that vision changes, that the immune system weakens, that cognitive function can be affected. We know that exercise is crucial to maintain muscle and bone mass. We know that psychological support and communication with loved ones back home are essential for mental health. But the ISS is still in low Earth orbit. It's only about 250 miles up. The astronauts can see Earth out the window. They know that in an emergency, they could be home in a few hours. Mars is different. Mars is 6 months away at best. If something goes wrong, you're on your own. There's no abort to Earth option. You have to be self-sufficient, and that changes the psychological equation. This is where Interstellar's portrayal of space travel is perhaps most accurate in spirit, if not in detail. The isolation, the distance from home, the knowledge that you might not return. These are real psychological challenges that any interstellar mission would face magnified 1,000-fold. When the crew watches Earth recede to a pale blue dot and then vanish entirely as they enter the wormhole, that's not just a visual effect. That's a representation of the profound psychological leap required to leave everything you've known behind. Now let's talk about something that keeps me up at night: the Fermi paradox. If the universe is so vast, if there are billions of galaxies each containing billions of stars, many with planets in the habitable zone, then where is everyone? This question was famously posed by physicist Enrico Fermi during a lunch conversation in 1950. The numbers suggest the universe should be teeming with life, and at least some of that life should have evolved to intelligence and developed technology. Some civilizations should be millions or billions of years older than ours. They should have had plenty of time to colonize the galaxy, to build megastructures we could detect, to send signals we could receive. So where are they? There are dozens of proposed solutions to the Fermi paradox, and they range from the mundane to the terrifying. Maybe life is rarer than we think. Maybe the jump from simple life to complex multicellular life is incredibly improbable. Maybe intelligence is rare, or technological civilization is a brief phase that civilizations pass through before destroying themselves or transcending physical existence. Maybe interstellar travel is simply too difficult, even for advanced civilizations, and everyone is stuck on their home world. Or maybe they're here, but we don't recognize them. Maybe advanced civilizations operate on scales or in ways we can't perceive. Maybe they're in the oceans or in forms we wouldn't recognize as life. Maybe they've deliberately hidden themselves from us, waiting for us to mature as a species. This is the zoo hypothesis, the idea that we're being observed but not contacted like animals in a wildlife preserve. Or, and this is the dark solution, maybe civilizations don't last long enough. Maybe there's a great filter, some challenge that almost no species survives. Maybe it's nuclear war or ecological collapse or an AI catastrophe or something we haven't even thought of yet. The terrifying question is the great filter behind us or ahead of us? If it's behind us, if the hard step was the origin of life or the evolution of intelligence, then we're past it, and the galaxy might indeed be ours to explore. But if it's ahead of us, if there's some challenge that awaits all technological civilizations, then our future might be much shorter than we hope. I don't know the answer. Nobody does. But I think about it when I look at our own civilization's challenges. Climate change, nuclear proliferation, engineered pandemics, artificial intelligence. We're creating risks that could end us. Are these the great filter? Are we in the critical period right now, where our fate hangs in the balance? If so, then every effort we make to solve these problems, every step towards sustainability and wisdom and cooperation, is literally a fight for the future of our species and possibly for the very concept of intelligence in the universe. But let's be optimistic. Let's assume we survive, that we're one of the civilizations that makes it through. What then? How do we organize ourselves for the long-term project of becoming an interstellar species? Here's where the Kardashev scale becomes relevant. This is a method of measuring a civilization's level of technological advancement based on the amount of energy it can harness. A Type 1 civilization can harness all the energy available on its planet. We're not quite there yet. We're at about Type 0.73 on the Kardashev scale. We use fossil fuels and renewable energy, but we're not capturing all the energy from our planet's geothermal heat, its moving water, its blowing wind, its incoming sunlight. A true Type 1 civilization would have no energy scarcity. They'd control weather, reshape continents, and have effectively unlimited power for their planetary civilization. A Type 2 civilization can harness all the energy output of its star. The classic example is a Dyson sphere, a megastructure that surrounds a star and captures all of its energy output. This isn't necessarily a solid shell, which would be mechanically unstable, but rather a swarm of solar collectors orbiting the star, intercepting its light and converting it to usable energy. A Type 2 civilization would have energy resources millions of times greater than a Type 1 civilization. They could construct massive space habitats, terraform planets, move worlds, possibly even manipulate stars. A Type 3 civilization can harness the energy of an entire galaxy. This is so far beyond our current capabilities that it's hard to even imagine. But we can speculate. Such a civilization might span thousands of star systems, with infrastructure connecting them. They might manipulate spacetime itself, create wormholes, harness the energy of supermassive black holes. They might be the mysterious they from Interstellar, the advanced beings who placed the wormhole near Saturn. The jump from Type 1 to Type 2 is enormous, requiring technologies and resource management far beyond anything we have. The jump from Type 2 to Type 3 is even more staggering. And yet, if we're serious about becoming an interstellar and eventually an intergalactic species, these are the paths we need to consider. We need to think on timescales of millennia and energy scales that dwarf our current consumption. One technology that bridges this gap is the space elevator. This is exactly what it sounds like, a structure extending from Earth's surface to geostationary orbit and beyond, allowing us to move cargo and people to and from space without rockets. The concept relies on a tether made of incredibly strong material, probably carbon nanotubes or graphene, anchored to Earth and counterweight by a station beyond geostationary orbit. Why is this important? Because rockets are expensive and inefficient. Every kilogram you want to send to orbit requires many more kilograms of fuel, which requires structure to hold that fuel, which requires more fuel to lift that structure. It's called the tyranny of the rocket equation, and it's why launching things to space costs thousands of dollars per kilogram. A space elevator, once built, could reduce that cost to dollars per kilogram. It would make space accessible in ways we can barely imagine. But we don't yet have materials strong enough to build a space elevator for Earth. The tether would need to withstand enormous tensile forces while being light enough that its own weight doesn't break it. Carbon nanotubes might work, but we can't yet manufacture them in the lengths and quantities required. However, a lunar space elevator is more feasible. The moon's lower gravity means much less demanding requirements for the tether material. A Martian space elevator is also possible. These could serve as stepping stones, proving the technology and providing infrastructure for further exploration. There's another megastructure concept that excites me: orbital rings. These are active structures that use magnetic levitation to support themselves in orbit. Unlike a space elevator, which relies on tensile strength, an orbital ring uses momentum and magnetic forces. A stream of high-speed projectiles or plasma circulates around the planet, held in place by magnetic fields. Tethers descend from the ring to the surface, providing access to space. Because the forces are distributed around the entire structure, the material requirements are much less demanding than for a space elevator. With orbital rings, you could have multiple access points to space around the planet. You could build massive orbital habitats, shipyards for constructing interplanetary and eventually interstellar vessels, solar power arrays beaming energy down to Earth. An orbital ring could be the infrastructure that finally makes humanity a true spacefaring civilization. And once we're spacefaring, we can access the resources of the solar system. Asteroid mining isn't science fiction. It's serious business. Several companies are already planning missions. Asteroids contain metals, water, and other resources worth literally trillions of dollars. A single metallic asteroid might contain more iron, nickel, and platinum group metals than humanity has mined in all of history. Water from asteroids can be split into hydrogen and oxygen for rocket fuel, making them natural refueling stations. The asteroid belt contains enough material to build habitats for a population far exceeding Earth's current population. Not planets, most asteroids are too small to have significant gravity, but rotating cylindrical or toroidal habitats that generate artificial gravity through spin. These O'Neill cylinders, named after physicist Gerard O'Neill who popularized the concept, could house thousands or millions of people in Earth-like conditions with forests and lakes and open skies, all inside a structure orbiting the sun. Imagine a future where billions of humans live not on planets, but in these space habitats scattered throughout the solar system. Each habitat could be a unique ecosystem, a different culture, an experiment in human society. You could have habitats optimized for research, for manufacturing, for agriculture, for art and recreation. The diversity of human civilization could explode beyond anything possible when we're confined to one planet. This is the vision of a Type 2 civilization beginning to emerge. But it's not just about energy and resources. It's about information, about understanding, about the accumulated knowledge of a species that's been studying the universe for millennia. What would such a civilization know? What mysteries would they have solved? They might have a complete theory of quantum gravity, understanding the fabric of spacetime at the deepest levels. They might know whether the multiverse exists, whether there are other universes with different physical laws parallel to our own. The concept of the multiverse comes from various sources in physics. In inflation theory, the rapid expansion of the early universe might have created countless bubble universes, each with potentially different properties. In quantum mechanics, the many worlds interpretation suggests that every quantum measurement splits the universe into multiple branches, each representing a different outcome. Are these real universes or just mathematical abstractions? We don't know, but an advanced civilization might. They might even find ways to detect or communicate with other universes if they exist. Imagine receiving a message from a parallel universe where history unfolded differently. In one universe, humans never evolved. In another, we destroyed ourselves in nuclear war. In another, we've already colonized the galaxy. If we could somehow compare notes across these universes, what could we learn? Even within our own universe, there are mysteries that an advanced civilization might solve. Dark matter makes up about 27% of the universe's mass energy content, and we still don't know what it is. We know it exists because we can see its gravitational effects on galaxies and galaxy clusters. The way galaxies rotate, the way they cluster together, the way light bends around them. All of this tells us there's far more matter present than we can see. But what is it? It's probably not ordinary matter made of protons, neutrons, and electrons. Observations rule that out. It's probably some new type of particle that interacts very weakly with ordinary matter. Physicists have proposed many candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos. Experiments are underway to detect these particles directly, but so far, we haven't found them. An advanced civilization might have solved this puzzle, might have even learned to manipulate dark matter, using it for purposes we can't imagine. And then there's dark energy, even more mysterious than dark matter. Dark energy makes up about 68% of the universe's mass energy content, and it's causing the universe's expansion to accelerate. Galaxies are moving away from each other faster and faster, and the culprit appears to be some form of energy inherent to space itself. The more space there is, the more dark energy there is, driving expansion. But what is it? Why does it have exactly the density it does? Is it constant, or does it change over time? One possibility is that dark energy is the cosmological constant, a term Einstein added to his equations and later called his greatest blunder. But the cosmological constant predicted by quantum field theory is wrong by a factor of about 10 to the power of 120. That's not a typo. The prediction is off by 1 followed by 120 zeros. This is the worst prediction in the history of physics. There has to be something we're misunderstanding about the vacuum energy of space or about how gravity works on the largest scales. Could an advanced civilization harness dark energy? If it's a property of spacetime itself, maybe they could manipulate it, creating regions where space expands or contracts on command. This could be another route to faster-than-light travel, not by moving through space, but by expanding space behind you and contracting it in front of you. This is, in fact, similar to how the Alcubierre drive is theorized to work. But we're speculating on top of speculation here, trying to imagine technologies based on physics we don't yet understand. Let me bring us back to something more concrete: the psychology of deep space. When you're months or years away from Earth, when the sun is just another star in the sky, what happens to the human mind? We have some data from Antarctic research stations and from submarines, environments that are isolated, confined, and dangerous. The research shows that humans can adapt, but it's hard. There's a phenomenon called the third quarter effect, where morale drops significantly when you're past the halfway point but not yet close to the end. People become irritable, depressed, less productive. For an interstellar voyage lasting decades or centuries, these psychological challenges multiply. Even if we use cryosleep, the crew who are awake need to remain mentally healthy. And if we use generation ships, we need to create stable societies in a closed environment. There will be births and deaths aboard the ship. People will live their entire lives without setting foot on a planet. How do you maintain culture, purpose, hope across generations when the destination is still years or decades away. This is where virtual reality might play a crucial role. Imagine crew members spending time in simulated environments that feel as real as Earth, walking through forests that don't exist, swimming in oceans that are just code. This could provide psychological relief from the confinement of a spacecraft. But it also raises questions. If the virtual world is indistinguishable from reality, what makes the physical destination special? Could a civilization decide that virtual worlds are preferable to physical exploration, choosing to remain on their home world and live in increasingly sophisticated simulations? This is another possible solution to the Fermi paradox. Maybe advanced civilizations turn inward rather than outward. Maybe once you can create perfect virtual realities, the messy, dangerous business of physical space exploration loses its appeal. You can experience anything you want, be anyone you want, explore infinite virtual universes without ever leaving your home planet. If that's the case, then the galaxy might be full of civilizations that are all looking inward, ignoring each other and the physical cosmos. I hope that's not our future. I hope we remain curious about the actual universe, not just simulated ones. Because there's something about physical reality, about actually being there, touching alien soil, breathing air you've generated from the atmosphere of another planet, seeing an alien sunset with your own eyes, something that I don't think can be replicated in simulation. The knowledge that it's real, that you're actually there, makes all the difference. Let's talk about another challenge: governance. How do you govern an interstellar civilization? Earth's nations can barely cooperate now, and we're all on the same planet with instant communication. How do you maintain political unity, or even just peaceful coexistence, when your civilization spans multiple star systems with communication delays of years or decades? The answer might be that you don't. An interstellar civilization would likely be fragmented, with each colony or cluster of colonies developing its own culture, government, and identity. Earth might be the ancestral home, remembered in stories and history, but not the seat of any central authority. Each colony would be largely autonomous by necessity. They'd have to make their own decisions, solve their own problems, adapt to their own local conditions. Over time, these colonies would diverge, not just culturally, but possibly biologically. Humans evolving under different selection pressures on different worlds might become different species. A human born and raised on Mars, with its low gravity and high radiation, would be adapted to those conditions in ways that might make them uncomfortable on Earth. A human on a high-gravity world would develop stronger bones and muscles. A human in a zero-gravity space habitat might become uncomfortable anywhere with significant gravity. This speciation of humanity would be slow, taking thousands or millions of years, but it's inevitable if we spread across the galaxy and stop interbreeding. Unless we use genetic engineering to maintain compatibility, which we might decide that being human means something specific at the genetic level and work to preserve that even as we adapt to new environments. Or we might embrace the divergence, welcoming the diversity of post-human species that could emerge. Imagine a future where the descendants of humanity include space-adapted humans with altered physiology, genetically engineered variants designed for specific environments, uploaded minds existing as software, cyborgs blending biology and technology, and perhaps even artificial intelligences we consider our children rather than our tools. All of these could trace their lineage back to us, to Homo sapiens on Earth in the 21st century, but they'd be as different from us as we are from our primate ancestors. Is that still humanity? That's a philosophical question without an easy answer. But I think the essence of humanity isn't in our specific genetics or even our biology. It's in our curiosity, our creativity, our desire to understand and explore. If our descendants, whatever form they take, still carry that spark, then in a meaningful sense, they're still human. Interstellar touches on this with the mysterious they, the beings who place the wormhole near Saturn. The movie heavily implies these are future humans, evolved beyond our current understanding, who have learned to manipulate space-time and higher dimensions. They're helping their ancestors survive, closing a causal loop. It's a vision of humanity's future that's both hopeful and strange. We survive, we transcend, we become powerful enough to manipulate the universe itself, but we're still connected to our origins, still caring about the survival of our past selves. Is this realistic? The science is speculative, but the sentiment resonates. We are the product of an unbroken chain of life stretching back billions of years. Every one of our ancestors, from the first self-replicating molecules to our immediate parents, successfully survived and reproduced. That's an extraordinary legacy, and we have a responsibility to continue that chain, to give our descendants a chance to exist, to flourish, to become whatever they might become. This is why the stakes in Interstellar feel so high. It's not just about saving the current population of Earth. It's about preserving the future, all the potential humans and post-humans who could exist if we don't go extinct. Every time a species goes extinct, it's a tragedy. But when a species with our level of consciousness and potential goes extinct, it's a cosmic tragedy. We're not just animals trying to survive. We're the universe's way of understanding itself, and if we disappear, that understanding disappears with us, at least in this corner of the cosmos. So we can't afford to fail. We can't afford to let short-term thinking, tribalism, greed, or fear prevent us from solving the challenges that threaten us. Climate change, nuclear war, pandemics, AI alignment, these are the tests we face in this century. And I believe we'll pass them, not because the universe owes us survival, but because we're capable of rising to challenges when we recognize what's at stake. Look at what we've accomplished already. In just a few thousand years, we've gone from hunting and gathering to splitting atoms and sequencing genomes. We've gone from thinking Earth was flat and the stars were tiny lights on a celestial sphere to understanding the universe's history back to microseconds after the Big Bang. We've gone from being trapped on one continent to landing on the moon. The pace of progress is staggering, and it's accelerating. The scientific revolution began just a few centuries ago. The Industrial Revolution was just 2 centuries ago. The Information Revolution was just decades ago. Each revolution happens faster than the last. There's every reason to think the pace will continue, that the next century will see advances we can barely imagine. Quantum computing, synthetic biology, nanotechnology, artificial intelligence. These fields are all at the early stages, promising revolutions of their own. By the end of this century, we might have fusion power providing unlimited clean energy. We might have nanomachines that can repair our bodies at the cellular level, effectively ending aging. We might have artificial superintelligence helping us solve problems beyond human comprehension. We might have colonies on Mars and the Moon. We might have sent probes to nearby star systems. We might have detected signs of life on exoplanets. Or we might have destroyed ourselves. The same technologies that could save us could also doom us. That's the nature of powerful technology. It amplifies our abilities, for good or ill. A hammer can build a house or crush a skull. Nuclear fission can power a city or destroy one. The question is always, who's wielding the tool and what are their intentions? This is why education, ethics, and wisdom are just as important as technology. We need scientists and engineers to create the tools, but we also need philosophers and ethicists to guide their use. We need educated citizens who can make informed decisions about how our species should proceed. We need leaders who think beyond the next election cycle, beyond national borders, beyond their own lifetimes. We need to think like ancestors, not our ancestors, but the ancestors of future generations. What would they want us to do? What world would they want to inherit? I think they'd want us to preserve Earth's biosphere, to solve climate change, to develop sustainable technologies. They'd want us to avoid existential risks, to ensure that they get a chance to exist at all. And they'd want us to explore, to expand, to give them a universe to inherit, not just a single planet. That's the long view. That's thinking on timescales of centuries and millennia. And it's hard because our brains evolved for immediate threats and rewards. We're good at thinking about tomorrow or next year. We're not naturally good at thinking about the next century. But we have to learn because the decisions we make now will echo through the ages. Interstellar understands this. The movie's central relationship between Cooper and Murph spans decades. The love between a father and daughter transcends time, becomes the emotional anchor that saves humanity. It's a beautiful metaphor for the intergenerational project of civilization. We make sacrifices for people we'll never meet, people who don't exist yet. We plant trees whose shade we'll never sit in. We invest in research whose benefits won't arrive for decades. We launch probes that will reach their destinations long after we're dead. Why do we do this? Because we can imagine the future. Because we care about more than just ourselves. Because we recognize that we're part of something larger, a chain of being that extends backward to the origin of life and forward to possibilities we can barely conceive. That capacity to care about the future, to make sacrifices for abstract principles and distant benefits, that's uniquely human as far as we know. It's one of our greatest strengths, and we're going to need that strength for what comes next. The challenges ahead are immense, but so are the opportunities. We stand at a pivotal moment in history. For the first time, we have the capability to destroy ourselves completely. But for the first time, we also have the capability to become something more than we are, to spread beyond our planet, to reach for the stars literally rather than metaphorically. Which future we get depends on the choices we make. Every single one of us contributes to that outcome. By how we vote, how we spend our money, how we treat each other, how we think about the future, what we teach our children. It all matters. You matter. Your choices ripple outward in ways you can't always see, influencing others, changing probabilities, shifting the trajectory of history in tiny but real ways. So make good choices. Choose curiosity over fear. Choose cooperation over conflict. Choose long-term thinking over short-term gains. Choose hope over despair. Not because the universe guarantees a happy ending, it doesn't, but because hope is what motivates us to create that ending ourselves. The universe is vast and ancient and will continue with or without us. But right now, we're here. We exist. We have consciousness and agency. We can shape the future, at least our corner of it. And that's not nothing. That's everything. When I look up at the night sky, I see the past. The light from those stars left them years or centuries or millennia ago. Some of those stars might not even exist anymore. But I also see the future, because somewhere around some of those stars might be planets where our descendants will live. Somewhere in that vast darkness, there are places that will become new homes, new Earths, new chapters in the story of humanity and whatever comes after humanity. We're writing that story right now. Every discovery, every mission, every step toward understanding and exploration is another sentence in that story. And it's going to be an incredible story, full of challenges and triumphs, failures and breakthroughs, tragedy and joy. It's going to be the greatest adventure in history, spanning not just continents or oceans but light years, not just years or decades but millennia and beyond. And you're part of it, just by being here, by being human, by being curious about these questions. You're part of the generation that will determine whether that story continues or ends. Whether we reach the stars or confine ourselves to one planet, whether we survive our own power or succumb to it, whether we become a Type 1, 2, 3 civilization or fade into extinction, leaving no trace except fossils for some other species to puzzle over millions of years from now. I know which outcome I'm rooting for. I'm rooting for us. I'm rooting for humanity to pull together, to solve our problems, to reach beyond ourselves and touch the cosmos. I'm rooting for a future where children grow up learning not just about the countries of Earth, but about the planets of the solar system and the star systems of the galaxy. Where the question, what do you want to be when you grow up, might be answered with an asteroid miner or a terraforming engineer, or a pilot on the Mars-Europa route, or an exoplanet biologist. I'm rooting for a future where the words home planet means something specific, where humans born on other worlds visit Earth as tourists, marveling at the rich biosphere and feeling slightly uncomfortable in the unfamiliar gravity. Where the question, where are you from, might elicit answers like Titan or New Terra or Station Orbital 7 or Proxima Colony. That future is possible. Not certain, but possible. And possibility is all we need to work with. We've always worked with possibility. Our ancestors didn't know if they'd survive the winter, if the crops would grow, if the journey across the ocean would succeed. But they tried anyway. They took risks, made sacrifices, pushed forward into uncertainty. And here we are, the beneficiaries of their courage and determination. Now it's our turn. Our turn to be brave, to take risks, to push forward. Our turn to solve impossible problems and achieve impossible things. Our turn to prove that human beings, for all our flaws and limitations, are capable of wisdom and greatness. The real interstellar isn't waiting for us in some distant future. It's happening now, in the labs where scientists are pushing the boundaries of knowledge, in the mission control rooms where engineers are guiding spacecraft to distant worlds, in the observatories where astronomers are discovering new planets, in the schools where children are learning about the universe and dreaming of exploring it, in the conversations where people debate how to address climate change, develop ethical AI, prevent nuclear war. In the quiet moments when someone looks up at the stars and feels that ancient call to explore. It's all connected. It's all part of the same story. The story of intelligent life emerging from the cosmic void, achieving understanding, reaching beyond its origins, and ultimately making its mark on the universe. Not by conquering or dominating, but by exploring, understanding, creating. By being curious and caring and courageous. That's the story I want us to tell. That's the future I want us to create. Not just for ourselves, but for all the generations to come. For the children who will grow up on other worlds. For the scientists who will make discoveries we can't imagine. For the explorers who will see sights no human has ever seen. For the philosophers who will grapple with questions we haven't thought to ask. For the artists who will create beauty inspired by alien landscapes. For everyone who comes after us, building on what we did, going further than we ever could. We owe it to them. We owe it to ourselves. And in a strange way, we owe it to the universe itself. The universe created us through billions of years of physics and chemistry and evolution. It gave us consciousness, the ability to understand it. And now we have a responsibility to use that gift, to push the boundaries of understanding, to explore, to endure, to ensure that this brief flicker of awareness in the cosmic darkness burns as brightly and as long as possible. So yes, let's go to the stars. Let's solve our problems here on Earth first, absolutely. Let's make sure we survive to see the future. But let's never lose sight of that ultimate horizon, those distant lights calling us onward. Because humanity has always been about reaching for the next horizon. This is who we are. This is what we do. And this time, the horizon isn't just beyond the next mountain or across the next ocean. It's beyond our solar system, our galaxy, maybe even our universe. It's as far as imagination and physics and determination can take us. And I, for one, can't wait to see how far that turns out to be. The journey of 1,000 light years begins with a single step, and we've already taken so many steps. We've left footprints on the moon. We've sent our machines to the edge of the solar system and beyond. We've peered into the depths of space and time, seeing galaxies as they were billions of years ago. We've split atoms and decoded genes and built computers that can beat us at our own games. We're capable of extraordinary things. We always have been. And now, standing at this pivotal moment in history, we get to prove it again. We get to show the universe and ourselves what humanity can do when we set our minds to something truly ambitious. When we think not in terms of quarters or election cycles, but in terms of centuries and millennia. When we work not for personal gain, but for the collective future. When we choose hope and curiosity and courage over fear and apathy and despair. The stars are waiting. They've been waiting for 13.8 billion years, and they'll wait for billions more. But we won't wait. We can't wait. Because every day we delay is a day we could have been learning, exploring, growing. Every problem we solve is a step toward that starfaring future. Every child we inspire is a potential scientist or engineer or astronaut who will take us further. Every bit of knowledge we gain is a building block for the technologies of tomorrow. This is our time. This is our challenge. This is our opportunity to be the generation that didn't just survive but thrived, that didn't just endure but explored, that didn't just exist but reached for something greater, to be the ancestors that future generations will remember with gratitude and awe, the ones who made it possible, the ones who kept the dream alive, the ones who took the steps necessary to ensure there would be future generations at all. So let's do it. Let's solve climate change and develop fusion power and build lunar bases and send humans to Mars. Let's find signs of life on exoplanets and create AI that augments rather than replaces human intelligence. Let's address inequality and education and governance. Let's make Earth a place worth returning to even as we venture beyond it. Let's become the species we have the potential to be: wise, curious, compassionate, and boundlessly ambitious. Let's prove that Interstellar wasn't just a movie but a prophecy, that humanity does survive, does explore, does reach the stars and beyond, that love and hope and determination really are powerful enough to overcome any obstacle, that the equations can be solved, the challenges met, the impossible made possible. Let's look back from the future and be proud of what we accomplished. Proud that we didn't give up when things got hard. Proud that we thought beyond ourselves and our immediate needs. Proud that we preserved the beauty of Earth while reaching for the stars. Proud that we created a civilization worthy of the cosmos, capable of understanding it, exploring it, and maybe eventually shaping it. The universe is vast and full of wonders. And now, after billions of years of unconscious physics, a small corner of it has become aware. We are that awareness. We are the universe experiencing itself, and that's the most extraordinary thing of all. Not just that we exist, but that we know we exist. Not just that we're here, but that we can ask why and how and what's next. So what's next? The stars, the galaxy, the universe, whatever comes after, all of it, everything. The greatest adventure in history is just beginning, and we get to be part of it. Not just as observers, but as participants, as pioneers, as the generation that makes it happen. The real Interstellar starts now. With us, with you, with the choice to believe that despite all the challenges, despite all the unknowns, despite all the reasons for doubt, we can do this. We will do this. We must do this. Because the alternative, giving up on the dream of exploring the cosmos, giving up on the future, giving up on our potential, is unacceptable. It's not who we are. It's not who we're going to be. We're going to the stars. Not today, not tomorrow, but eventually, inevitably. Because that's what humans do. We explore. We discover. We push boundaries. We reach for the impossible and make it real. And nothing, not distance or time or the laws of physics themselves, will stop us. We'll find a way. We always do. So look up at the night sky one more time. See those stars, those distant suns, some with planets orbiting them, maybe with life, maybe with civilizations of their own looking back at us across the cosmic gulf. Know that one day, whether it's decades or centuries or millennia from now, humans or our descendants will visit some of those stars. We'll stand on some of those planets. We'll look up at their alien skies and see our sun as just another distant point of light. And when that happens, when that incredible moment arrives, it will be because we made it possible. Because we didn't give up. Because we chose hope over fear, knowledge over ignorance, exploration over stagnation. Because we were human in the best sense of that word. Curious, brave, determined, and endlessly, impossibly ambitious. That's the real Interstellar. That's our future. That's our destiny, if we choose to seize it. And I believe we will, because we have to, because we can, because the stars are calling, and we've never been able to resist that call. The journey begins now. The adventure continues. The story unfolds, and you're part of it. Every single one of us is part of it. The greatest story ever told. The story of life reaching beyond its origins to touch the infinite. Welcome to the real interstellar. Welcome to the future. Welcome to the stars. Let's go make history. Let's go change the universe. Let's go home to all those distant worlds that are waiting for us, that have always been waiting for us, that we've been dreaming about since we first looked up and wondered what those lights in the sky might be. The answer is, they're our future. They're where we're going. They're what we're reaching for. And nothing in the universe will stop us from getting there. Nothing at all.